Welcome to week 6. The good news is we're over the halfway part for our course and our time together. The other good news is a lot of students find the material around correlation and regression to be a lot easier than the ANOVA content. In my opinion, I think the ANOVA chapters are the hardest ones in the book, so usually the course gets a little bit easier from here on out. So if you struggled a little bit with ANOVA, hopefully this will be a refreshing change of pace. So this will cover chapters 12 and 13. In your textbook, we'll talk about correlation and regression. We're really switching gears conceptually because up until this point, we've been focusing on a dependent variable. That's something we can take the mean of. So it's scale or continuous or interval ratio, whichever of those many terms you want to use. And we've been focusing on categorical or nominal predictors or independent variables. So the t-test looked at an IV that had 2 levels, 2 categories. The ANOVA was able to take on more than 2 categories. We also talked about between groups and within groups design and how that can create variations on the ANOVA or the t-test. So correlation and regression is really going to focus on only continuous or interval level variables. So no nominal variables, no categories. That's not to say that you can't use those type of variables in correlation or regression, but we won't focus on that for this part of the course. It's a little more in depth than we're able to get into at this time. So to kind of set the stage, I really like talking about scatter plots because it helps us really conceptualize what a correlation is and what it's actually testing and getting at. So you can see here just a really simple example of a scatter plot. You have a couple people here, 6 people in the sample, persons A through F. You have some kind of score on variable X, some kind of score on variable Y. And you can see, for example, person A, they scored a 1 on X and a 1 on Y. So I can take those coordinates and plot them on a scatter plot. And you can see I did this for every single person in this little mini sample. So you can see kind of the line goes across for person C. We would go across the x-axis or the horizontal axis by 3 units, and then we would go up the y-axis or vertical axis by 2 units, plot the point, and you can kind of see it there. So the scatter plot is a nice way to visualize our correlation, and really I like to use scatter plots as kind of a pre-screen to make sure that I have a good understanding of what's going on in my data set and whether or not a correlation is even an appropriate test to be using. When we're looking at a scatter plot, there are a couple considerations we might think about when we're interpreting them. One is the overall form of the relationship, so whether the dots appear to form a straight line or a curve or some other shape. The second is the direction of the relationship, whether the dots are moving in a positive or a negative direction. And the third is the strength of the relationship. And I think of this as how kind of tightly clustered the dots are together versus kind of spread out all over the place. So the first point here, the form of the relationship, it's important to point out here that our correlation coefficient is best used for linear data. So we would want those dots on the scatter plot to fairly closely resemble some kind of straight line pattern. So they won't line up perfectly, but we like there to be some kind of general linear trend as opposed to a U or a horseshoe or a circle or anything else kind of non-linear. To say a little bit more about the second bullet, the direction of the relationship, you really want to think about which direction your variables are moving. So if your variable is increasing or moving towards the positive numbers on the x-axis and also moving towards the positive numbers on the y-axis, we would call this a positive relationship. If our variables are moving in opposite directions, meaning as one increases, the other one decreases, we would refer to that as a negative relationship. So this can get a little bit confusing, so let's talk through a couple of examples here. Let's say that I'm interested in the relationship between, I think that the amount of time someone spends exercising is related to how much they weigh. So you could imagine I might measure amount of time spent exercising in hours or minutes, number of times per week. And I think that as that number gets bigger, the more time spent exercising, you would expect your weight to decrease. And again, we would measure weight maybe in pounds or something like that on that continuous scale. So as hours spent exercising increases, your weight in pounds is decreasing. So this is an example of a negative relationship because as one is going up, the other is going down. It can be a little bit confusing because that relationship in itself, it sounds like a good thing. It has kind of a positive connotation to it. But in statistics, we're really just thinking about the direction of the relationship, or excuse me, the direction of the variables if they're moving together or separately. So if that's an example of a negative relationship, a positive relationship might be the more times you go out and eat fast food, the more your weight will increase. So again, that sounds like kind of a bad thing to happen to you, but this is an example of a positive relationship because the amount of time you're spending going out to eat is also associated with your weight going up. So both of the variables are moving together in some kind of relationship or pattern. So the positive and negative can kind of throw people off, but just try to think of a couple of examples of whether variables are moving together in the same direction or in opposite directions. And again, just to reiterate, the third bullet, the strength of the relationship, if our dots on the scatter plot were lined up in a perfectly straight line, that would indicate a very strong relationship. If they're kind of scattered randomly throughout the plot, that would be a much weaker relationship. So here's a blast from the past. It's been a couple weeks since we've talked about z-scores. But if you remember our discussion on z-scores, the whole point was that we can measure variables using different measurement units. So talking about measuring weight in pounds, measuring height in inches, measuring attitudes on a 7-point scale or a 10-point scale. We can measure things in an interval, ratio, or continuous way using lots of different measurement units. But in order to make comparisons, we said we like to standardize them or create z-scores. So this is just a little reminder. Here we have a distribution of data. We'll say that they're test scores. You can see the center of the distribution or the balance point is a 70% in the course. That's our mean. And you can see that I've indicated the standard deviation for this test was 10 percentage points, 10 points on the exam. So if I scored an 85% on the test, I would have a z-score of 1.5. So again, it tells me that I'm above the mean, and I'm above the mean by about 1.5 standard deviations relative to the rest of the class. So our z-scores are kind of making a comeback here because that's how we calculate our correlation coefficient. So here we have the formula for calculating our correlation coefficient. I know formulas usually aren't people's favorite thing, but this one's actually not too bad when we dig into it. So the correlation coefficient, or we sometimes call it the Pearson product moment correlation, is designated by lowercase r, so little r. And you can see here that little r equals, the sigma Greek letter indicates the sum, and in the parentheses we have the cross products of z-scores on our x variable and z-scores on our y variable. And the sum of those cross products are then divided by the total number of participants or subjects we have. So basically, it's taking the average of the cross products on two variables. So let's go ahead and look at an example to try to break this formula down a little bit more. Again, we will not calculate these by hand, but I think it helps you understand from a conceptual level where we're coming from with the correlation. But again, we'll use SPSS to calculate these. Your book has a nice example that they use to walk you through calculating a correlation. It starts on page 168 in your text in chapter 12. I kind of took that example. Their example is the amount of time spent studying will correlate with exam score. So increasing the number of hours you spend studying will result in an increase in exam score. So I picked a slight variation on that. This is one that I think if you've taught high school students or college students, they might be more interested in this. But the idea is skipping class related to statistics grade. So kind of similar to the example in the book, a little bit of a different spin on it. You can see here that I have 10 students, and I've noted their absences for a semester as well as their final exam grade. So you can see student number 1, they missed class 4 times, they got an 82% on the exam. Student 6 missed 0 times, they got a 99%, very impressive. Student 8 missed 8 times throughout the semester and ended up with a 58%, not terribly surprising. So in order to compute a correlation coefficient, our very first step would be simply finding the mean and standard deviation of both of these variables. So you can see here, you can try it on your own, but I've kind of done a little shortcut here and calculated it for you. If we take the total, all the absences, sum them up, and divide them by 10 students, I get an average of about 3.4 absences during the semester and a standard deviation of 2.375. Similarly, with exam grade, if we take the average of this column, I get a 76% and a standard deviation of about 15.04 points or percentage points on the exam. So you could do that by hand, you could do it in Excel, you could do it in SPSS. There's kind of a couple ways you could approach this. But the very beginning calculations here, not too bad. We covered these really early on in the semester. Before we jump into calculating the correlation, I said I always like to start off with a scatter plot. So I've just drawn a quick one here with our absence and exam grade data. And I'll go ahead and plot in the average. I'm just going to draw a line at 3.4 absences, which was our average number of absences, and then a horizontal line for our average exam grade. That was 76%. So this kind of divides our data into kind of 4 quadrants here. And you can see in general, students who scored above average on the exam, who are above that horizontal blue line up in here, these tend to be students who were below average in number of absences, so the number of days they missed class. You can see we have an exception here. This person was above average in absences, but still did pretty well in the course. But in general, the students tend to be falling into this quadrant here. Similarly, if we tended to have above the average number of absences in the course, they tended to score below average in terms of their exam. Again, with the exception of this person over here, they didn't miss too many times, but still didn't do so great on the exam. But in general, you can kind of map out using the 2 averages where students fall in kind of one of these 4 different quadrants. The scatter plot gives us kind of a nice reference point for visualizing our data. We can also tell from the scatter plot that we have a negative relationship happening here. So as absences are increasing or going up, you notice our blue dots here tend to be going down in terms of exam grade. So absences increasing, exam grade is decreasing. You could also flip that around and say as absences are decreasing or getting smaller, or your exam grade is going up or getting higher. So that's a good example of that negative relationship. You could also see if we were to draw kind of a circle to encompass all of our points, it would be kind of a skinny oval shape that we could kind of draw a line through. So it's getting at that general linear pattern. It's not perfect, especially since we know we have these kind of anomalies in the other quadrants here, but overall it's kind of following that general linear pattern. Let's go ahead and see how we might calculate our correlation coefficient. So again, this is the same as the previous slide. This just has the 10 students, their individual score on absence and exam grade. I calculated the mean and standard deviation. So the next step on our correlation coefficient equation is we need to calculate z-scores for absences as well as z-scores for exam grade. So on this slide, again, if you remember from z-scores and our discussion on that, I'm just going to take each student's individual raw score, subtract the mean, and divide by the standard deviation. So just to click back once here, student number 1 had 4 absences. I would subtract 3.4 and divide by the standard deviation of 2.375 and end up with a z-score of 0.253. Which makes sense because that person is slightly above average in terms of their absences, so that's why it's a positive z-score. So I just replicated that process down the entire column for absences. The second step then was to do the same process for z-scores. So here, or excuse me, for exam grade. So here you want to make sure that you swap out your mean and standard deviation. So now I'm taking the exam grade for student number 1, subtracting that class average of 76 and dividing by that standard deviation of about 15 percentage points. And I would do that for every single person as well and just work my way down the column. So we only have 10 people here, so it's not terribly tedious if you wanted to try this by hand, or you could even do it in Excel with some formulas. But if you get much larger of a sample, this gets a bit tedious to do by hand. So that's why we'll use SPSS, but conceptually, all I've done is convert my raw absences and raw exam grades into z-scores. So then we remember on our formula, we multiplied the absence or z-score of x by the z-score of y, in this case exam grade. So all I'm doing is multiplying these two variables for each person or each case. So 0.253 times 0.399, I get a cross product here of 0.101. So I will just do this for every single row. So I've calculated the cross product for each student. I can sum that, so I can add up this column and I would end up with a negative 8.511. That's giving me the numerator of that correlation coefficient, the numerator, the top of the equation. And if you recall, the last step was to divide by the total number of participants, or by n. And in this case, I have 10. So if I take negative 8.511 divided by 10 people, I end up with an R, or a correlation coefficient, of negative 0.85. So again, that's just kind of a quick idea of how we can calculate that by hand. I'll show you in a couple minutes here how we can do that in SPSS. So we have this little R value, this correlation coefficient of negative 0.85. Let's dig in a little bit more into what that actually means. So one thing that's kind of interesting about our correlation coefficient, or little r, is that it will always be between a -1 and a +1. It results in what we call a bounded value. So if you were to calculate a correlation by hand and you end up with 3.579, that should be a red flag that you did something wrong, because it will always range between a -1 up to a +1. So the sign of the correlation coefficient, the positive or negative, tells you whether the relationship is a positive or negative one. So whether your two variables are moving together in the same direction or if they're moving in opposite directions. And the actual value, or the number, tells you about the magnitude of the relationship. So in this case, -1 would indicate a perfect negative relationship. +1 indicates a perfect positive relationship, and 0 indicates absolutely no relationship. So the closer your number is to one of those ones, either the positive or negative, the stronger the relationship is, and the closer you are to 0 as kind of that middle point of your possible range of values, the weaker the relationship is. So a correlation, in our case, we have negative 0.85. That's fairly strong. It's getting close to that -1. A positive 0.85 would be equal magnitude. It would be the same strength correlation. They're just in different directions. On page 166 in your book, there's a table at the very bottom that kind of gives you some guidelines as to what constitutes a strong versus very strong versus moderate correlation. I would tell you to take that information with a grain of salt, as it tends to vary quite a bit from field to field. So what's considered a strong correlation in the medical field is maybe not the same thing as in the education field. So know that each field has kind of its own standards as what constitutes positive or negative, or excuse me, strong or weak correlation. Here we have just an illustration on, again, this idea of direction and magnitude. So you can see here, figure A, the relationship between beer sales and temperature. As temperature is increasing, the amount of beer sold is also increasing. So that's our positive relationship. Conversely, for figure B here, we have the relationship between coffee sales and temperature. So in this case, as temperature is increasing, you can see the amount of coffee sold is going down. So just another example to help you keep this idea of direction, positive or negative relationship straight in your mind. Here we have a couple of examples of magnitude. So again, a perfect positive correlation would be something like this, where the dots are really in that kind of perfect straight line going across the matrix. A positive 0.8 correlation, you can see there's a little bit more spread on the dots. A 0.3 positive correlation, we have more spread. And at 0 correlation, you can see here there's just no rhyme or reason to this pattern. The dots are kind of all over the place. And then the pattern kind of repeats itself when we look at the correlations in the negative direction. There's also a couple of interpretational issues we might want to consider. So I've said a couple times now that correlations are really only useful for linear relationships. SPSS, though, it'll calculate a correlation for you regardless of whether it's linear or nonlinear. It doesn't really know the difference because it's a computer program. Likewise, you could calculate it by hand. So it's really kind of up to you to know whether or not the correlation is the most appropriate test to use. You can see here on this top graph, we have kind of a linear relationship, and then we have this weird little curve, kind of an upper boundary at the top where it kind of cuts off. Down here we have kind of a rainbow shape where we have a peak point somewhere in the middle and then low ends on the sides there. And here we kind of have a U shape. So these are all examples of nonlinear relationships. Again, we could calculate a correlation for this, but it might not be the best choice. There are ways to calculate nonlinear relationships in SPSS. We just won't be getting into that in this course. It's a bit beyond our scope. The other interpretational issue is something that we call either truncated range or sometimes called range restriction. So the idea behind this is that depending on how we're measuring our data, we may not be getting the entire picture of what's going on. So here we have the relationship between GPA and SAT score. As you can imagine, people with high SAT scores tend to have high GPAs. We have that positive relationship. Both variables are moving upward together. And you could see if we calculated a correlation, we have kind of a nice linear pattern here. However, if we were to draw some kind of boundary or cutoff, let's say we're only interested in students who score above a certain level on the SAT, that might change how our correlation turns out. And you can see this graphic here on the bottom, I'm showing only those top performers, and that linear trend is a lot weaker. This almost just kind of looks like a circle of dots. It's harder to see that nice linear relationship that we see when we look at the entire range of scores. So range restriction can be important, and you can imagine in your own research, let's say if you were looking at scores on a personality assessment or maybe a satisfaction survey, people who are really highly satisfied and all their scores are very high and similar, it might be harder to find a relationship or a correlation that exists if you don't have a full range of potential scores in your sample. It can truncate your results. The other issue to point out is that outliers, again, back to haunt us, outliers can also affect our correlation coefficient. So here we have an outlier really out by itself in the negative direction on both variables. We have kind of a circular cluster over here on the high range. If we were to look solely at this cluster, it's kind of a perfectly round chocolate chip cookie, so we probably wouldn't find a very large correlation. However, the addition of this outlier is going to create kind of this false linear relationship that doesn't really exist. And we would probably get a stronger correlation coefficient than had we just looked at these scores. Likewise, on the right-hand side here, we have a pretty nice linear trend going upward, but we have an outlier way up here. So if we were to calculate a correlation coefficient, it might be a fairly weak one because this outlier is kind of ruining this beautiful linear trend that we have. So again, a really good conceptualization and rationale for why we should plot our data in scatter plots and why that outlier screening is really important for us to take into consideration before we run our analyses. The final issue of our interpretation for our correlation coefficient is kind of this whole idea of which came first, the chicken or the egg. So in other statistics that we've run thus far, we've been really clear about saying what is our IV and what is our DV. And in a correlation, we're really looking at the association between two variables. So it's not always necessary to define which is the IV, which is the DV, because in some respects they're a bit interchangeable. For example, with our example of is skipping class related to grade, it could be that skipping class is our A variable. We think it comes first, and we think skipping class negatively affects your grade, which makes kind of logical sense. On the other hand, though, it could be that a student is doing poorly in their class. Maybe they receive a poor exam grade, B, and that in turn harms their motivation, and they kind of give up and stop coming to class, and therefore result in a larger number of absences, A. So that seems maybe a little less likely logically, but you could definitely make an argument either way, which is creating the issue. Or it could be that a third variable, C, is causing both effects. So maybe the student has something going on in their personal life. Maybe they're not getting enough sleep at night, and that's causing them to miss school a lot, and it's also causing them to do poorly on their exam. So the tricky thing with a correlation is it's sometimes hard to put this direction on it, whether it's A causing B, B causing A, or C causing A and B together. So it definitely gets a bit tricky with interpretation. And when we move on to the next chapter and talk about regression, we'll talk about how we can really define our independent and dependent variable. And instead of just talking about an association, we'll talk about actual prediction. So just know that for now, one of the limitations of our correlation coefficient is kind of this interpretational issue and not knowing which came first. So you'll frequently hear, I think it's become a bit of a buzzword, this idea that correlation does not equal causation. And this is just kind of a funny example. For example, there's a strong positive correlation between the number of films Nicolas Cage has appeared in and the number of people who drown by falling into a swimming pool. And someone has calculated this correlation at a positive 0.67. So this actually comes from a website down here, this Tyler Vignan. I think he was a graduate student at the time at Harvard, so he had a lot of free time on his hands. But he created this website, and you can read more about it if you click the hyperlink. But it's what's called spurious correlations that don't really make any sense. So he has all this publicly available data that he's aggregated about unusual causes of death, statistics from the CDC, various public data sets, and he's kind of put them together in a giant website, and you can really correlate anything with anything else. So if you're looking for something to do over the weekend, it's kind of an interesting website to play around with. And it's also a good illustration that, again, if you have a large enough sample size, you can really find a relationship or an association between any two random variables. So really the key here is being able to interpret it, and that's when we would even go back and look at the literature, what other people have found, in order to have a better understanding of the pattern we're seeing in our data and why it may or may not make sense. So here we have some SPSS shortcut commands. I'm going to jump over to SPSS and we'll look at how to put in a scatter plot as well as how to look at our correlation coefficient. The last thing I want to say before we jump over to SPSS is that your book does talk about variations on the correlation. So they talk about correlations that can be done with ordinal or rank order data. So know that there are different types of correlations. The Pearson correlation is definitely the most common, so that's why I've chosen to focus on that. But if you're interested in reading more about it, you can definitely run the other types using SPSS. It's not too terribly hard. So I'll go ahead and jump over to SPSS and we'll look at how we can run this using these commands. I went ahead and opened up SPSS. I input the same data that I walk through in the slides. So in case you'd like to try this example, again, you can try the one in your textbook as well. So I have absences, I have grade. I'm just going to click under variable view and make sure that I tell SPSS that my variables are scale. Everything else in terms of the name and decimal places looks good. So I'll go ahead and jump back to data view. So just as a review, we can certainly calculate our mean and standard deviation for these variables. And if you remember, that was under our Analyze menu, Descriptive Statistics, and Descriptives. So I can transport these over here and hit OK. And if you remember, it will give me my output window. We have here the mean standard deviation. These numbers should look very familiar, just like the example on the slide. I could even take this a step further. If you remember, we can compute z-scores in SPSS. That was when it created those new columns. But we'll go ahead and kind of skip that step and just look at how we can calculate a correlation coefficient. So I'm going to go ahead and use the Analyze menu again, and I'm going to drop down to this one called Correlate. So here I'm going to choose bivariate because again I'm working with two variables at a time. Some of these other menus your book talks about a little bit, but we will only use Analyze, Correlate, and Bivariate. And all you need to do here is pick which two variables you want to correlate and transport them over to the box on the right hand side here. You can see here the default is the Pearson correlation. Again, if you wanted to run some variations that your book talks about, you could certainly select those. The test of significance, again, we're always going to use a two-tailed test in this course. And you can see it also has this option checked where it's saying it's going to flag significant correlations. So that's kind of a nice feature. It'll put a little star next to the ones that are considered significant. So I will leave all these kind of default settings the same. I'm not going to change anything. I just transported my variables over and I'll hit OK. So you can see here the output, it's just this small little box and it's really kind of a matrix because if you see here we have absences. The Pearson correlation of absences with absences is 1. It's a perfect correlation, which we would expect. If we go over though, we have the correlation between absences and grade, which you can see here as a negative 0.851, which again should look very familiar. It's just like the one we calculated by hand in the slides. You can see it has these two little stars on it, and right below that value is a significance test. And you can see here, like our other statistical tests, we want this number to be as small as possible, and specifically we'd like it to be less than 0.05, which indeed this one is. We're at 0.002. The last thing that it does is it tells you the number of people that were in your sample that you ran the correlation on, which was 10. So same thing, the correlation between grade and absences, again, it's the same thing as the correlation between absences and grade. So it really kind of runs everything twice, which is a bit silly, but it did it so fast we won't really complain. And you can see down here with our asterisks, it's telling me that the correlation is significant at the 0.01 level. If you have just one star, you'll have a note and it'll say that the correlation is significant at 0.05. So SPSS is just trying to give you a little bit more information in terms of is your significance level at 0.05 or 0.01. So that's pretty easy to run. Again, that was just under Analyze, Correlate, Bivariate, and just transporting your variables. You can really correlate as many variables as you want, and it'll create a really large chart, and you can kind of see what correlates with what kind of relationships exist. The last thing that I want to show you is how we can generate a scatter plot to look at these. So here I'm going to go under the Graphs menu and select Chart Builder. And you've used this on a couple homework assignments before. I'm just going to close that extra box there. So really I'm going to look on the left-hand side. This is kind of the graph menu. We have bar graphs, line graphs, a whole bunch of different ones, pie charts. I'm going to click on Scattered Dot, and you can see here if I just kind of hover over this box, this is a simple scatter. So it's about as simple as you can get, just two variables. You can make kind of some really funky, fancy ones, but we're not going to go there right now. So I'm going to click and drag simple scatter into kind of this open white box up here. So here it's asking me to define my y and x axis. So it doesn't matter too terribly. Again, this goes back to the whole A leads to B leads to A issue. I'll go ahead and put absences though on the x-axis. That's how I had it in the slides. And I'll put grade on the y-axis. And then just hit OK. So you can see here it's generated a nice scatter plot for me. It looks a little bit different from the one in the slides, and you probably notice because on this y vertical axis the numbers start at 50 instead of 0. So we could actually double click this. So this will open up a new kind of editing window. So you can do some formatting things in here. For example, I could change the dots, I can fill them in. I could make them purple. That seems nice. You can click on the axes and kind of change the measurement units. You could change the font. You can bold. You can italicize. So you can kind of play around with the graph a little bit. There's some different features you can mess with. And then when you close it, it will save it kind of in the rest of your output. And then again, if you select and highlight this graph, copy and paste, it'll copy and paste really easily into a Microsoft Word document. You could also use, if you have a snip tool or take a screenshot, you can do it that way as well. So it kind of gives us that nice scatter plot. We can see again, just like in the slides, as absences are getting larger, your grade is decreasing and going downhill. So that's just how we run the correlation, both the actual computation of it, as well as how we can run a scatter plot to examine that relationship further. So there is a handout posted with the course documents that kind of walks you through in case you need a reference or didn't make it this far in the video. So hopefully that's helpful. If you run into any issues with it though, please feel free to reach out and let me know that you're having problems. So the next video, we'll kind of pick up where this one leaves off, and we'll get into regression and how we can use what we know about a correlation to make actual predictions. So that will be next time.